Waiting in line is part of everyday life because as year process, it has several important functions. Queues are a fair and essential way of dealing with flow of customers when there are limited resources. Negative outcomes arise if queue process is not established to deal with overcapacity. For example, way too many visitors navigate to a website. The website will slow and crash if it does not have a way to change the speed at which it processes requests or wait to queue visitor. Or imagine planes waiting for a runway to land when there is an exchange of planes. The absence of a queue would have real safety implications as planes all try to land at the same time. Queuing theory is important because it helps describe features of the queue like average wait time and provides the tool for optimizing queues. From a business sense, queuing theory informs the construction of efficient and cost-effective workflow. Queuing theory refers to mathematical study of the formation, function, and conjunction of waiting lines. This graph shows the relationship between service capacity and operating cost. Initially, cost of waiting in line is at maximum when organization is at minimal service capacity. As the service capacity increases, there is a reduction in the number of customers in the line and in their wait times, which decreases queuing cost. The optimal cost is found at the intersection between service capacity and waiting line curves. The principal actors in queuing situation are customer and the server. Customers are generated from the source or population. On arrival at a service facility, they can start service immediately or wait in a queue if if the facility is busy. When a facility completes a service, it automatically pulls a waiting customer from the queue. If the queue is empty, the, the, the facility becomes idle until a new customer arrives. From the standpoint of analyzing queues, the arrival of customers is represented by inter-arrival time between successive customers, and the service is described by service time per unit customer. Generally, the inter-arrival time and service time can be probabilistic. Queue size plays a role in analysis of queues, and it may have finite or infinite size. For example, queue length in a clinic is of finite size while call arriving at a telephone exchange is infinite. Here are some examples of customer and service facilities in different areas. For example, in a clinic, customers are patients, service providers are doctors, and queue problem is scheduling of patient in a clinic. Queuing discipline refers to the rules of the queue. For example, it behaves based on a principle for first in first out, last in first out, prioritized, or served in random order. Queuing theory is helpful in explaining the map behind how queue run. But when queuing theory is helpful in explaining the math behind how queues run. But when queues involves humans, queue psychology is important to understand. The queue experience as well. Customers can be patient or impatient, hence they show certain behaviors like barking when they don't desire to join the queue, jockeying when they decide to switch between the queues, reneging when they decide to leave the queue, finally the collusion, when several customers may cooperate and only one of them stand in the queue. There are different types of servers. Parallel servers, which we see in post offices, banks, or restaurants. Series servers, like in job processing in successive machines. Finally, the network, in which we can see it in routers in computer network. Queuing theory uses Kendall's notation to classify different types of queuing systems. Queuing systems are classified using the notation shown here, where the first element A is the arrival process, B is the mathematical distribution of the service time, C is the number of servers, D is the queuing discipline, E is the capacity of the queue, while F is the number of possible customers. The arrival and departure distribution can be denoted as M if it is Markovian, D if it is constant, Ek if it is gamma distribution, Gi or G if it is generic distribution. Queue discipline is denoted by FCFS, first come first served, LCFS, last come first served, SIRO, service in random order, GD, which is known as general discipline. For example, think of an ATM. If it can serve For example, think of an ATM. It can serve one customer at a time in a first in, first out order with a randomly distributed arrival process and service distribution time with unlimited queue capacity and unlimited number of possible customers. The queuing theory would describe the system as M/M/1 queue. Here you can see another example. Little's law is a formula that helps to operationalize queuing theory in many of its applications. It connects the capacity of queuing system and the average arrival rate into the system without knowing any other features of the queue. Here are some commonly used measures performance in queue situation. Lambda means the customer arrival, mu means the service rate, rho, which is a ratio of lambda and mu, also known as the service utilization factor or intensity of the traffic. LS and LQ, expected number of customers in system and queue respectively. WS and WQ, expected waiting time in system and queue respectively, and C bar is the expected number of busy servers. Consider a single server model with infinite capacity of source and queue length. The expected number of customers in the system is rho by 1 minus rho. The expected number of customers in the queue is rho square divided by 1 minus rho. The expected waiting time in the system is 1 by mu minus lambda, while waiting time in the queue is rho divided by mu minus 1 minus rho. Here, expected number of busy servers is rho. Consider a store with one counter with customer arrival rate 9 per 5 minutes and service rate is 10 per 5 minutes. Assume that the arrival rate is Poisson distribution and exponential for the service rate. Here, lambda is 1.8 per minute and mu is 2 per minute and rho is 0.9. Hence, the average number of customers in this system and queue is 9.9 and 8.1 respectively. The average waiting time in the queue and the system is 4.5 and 5 respectively. Queuing theory has been applied in many fields like telecommunication, transportation, logistics, finance, emergency services, computing, project management, etc. Here is the end of part 2 of the module 1.